Hello, everybody, and welcome to my Stars podcast. I'm your host, Ryan Webb, and today we'll be discussing the question, what are stars? Strap yourself in, kick your legs up, because we got a lot of content to cover. Let's get started. Our first topic today is astronomical measurements and electromagnetic radiation. Electromagnetic radiation is a type of energy that is more commonly known as light, and we can get from distant stars. Because the light we get is produced from electrons vibrating in particular atoms, we can analyze the radiation and deduce what elements are present in stars. Knowledge of how these elements release energy can tell us the star's surface temperature. Knowledge of the precession of nuclear reactions in stars can then be used to determine the star's age and mass as well. All of this just from gathering the star's electromagnetic radiation. There are 7 types of electromagnetic waves: radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. Since electromagnetic radiation is the same as light, and light travels in waves, all electromagnetic radiation travels at the same speed. This is represented by c, the speed of light, which is about 3 times 10 to the power of 8 meters per second. Moving on to calculations of wavelength, frequency, and period, wavelength equals a symbol called lambda, should be on the screen now, and it equals wave velocity divided by frequency, and it's measured in meters. Frequency is equal to f, and it can either be equal to 1 divided by period of the wave, which is equal to t, or wave velocity divided by wavelength. For electromagnetic waves, it equals speed of light divided by wavelength, and it's measured in hertz. For period, it's represented by t and equals 1 divided by frequency, and it's measured in seconds. Moving on to spectroscopy, it studies the interaction between matter and electromagnetic radiation that is derived from wavelength and frequency. It is mainly used as a tool to study atoms and molecules and can be used to investigate the light from stars. Spectroscopic data can be used to find many different things. In the diagram on screen, wavelength occupies the x-axis, while flux occupies the y. Some examples of how the data can be used is that the precise position at which the known emission and absorption lines are detected can be used to measure the redshift of an object. Another is that the width of both of the absorption and emission lines can be used to measure the average velocity of stars within galaxies. Finally, there is 3 different measurements used to measure the distances to stars and galaxies, and these are parallax, standard candles, and redshift. Parallax is a displacement or difference in the position of an object viewed from 2 different lines of sight and then measured by the angle of inclination between both lines. It is used to estimate distances in space with trigonometric parallax. They measure a specific star's movement against the stars that are further away as the Earth moves around the Sun. A good example of parallax in the real world would be looking out the window and seeing a road sign and a tree in the background. The road sign would go past quicker, but the tree would stick around for longer as it's further away. Standard candles are sources that have known luminosity and are used to measure further distances. Luminosity is a measure of radiant power from an object, or how bright something is, and is 3.84 times 10 to the power of 26 in this case. Light sources which are further away appear fainter because the light is spread out over a greater area. If we know how luminous something is, then we can estimate the distance from how bright it appears from Earth. The light that reaches Earth is spread out over a sphere, meaning that the radius of the Earth. Radius is the distance to the Earth. Finally, redshift is a concept where the wavelength is being stretched and the light is shifting towards the red part of the spectrum. It is used to measure approximate distances to very distant galaxies, as the universe expands, the space between galaxies is expanding. The more distance between us and a galaxy, the more quickly the galaxy will appear to be moving away from us. Our next topic today is the classification of stars, particularly the Sun. The Sun is a star because it produces its own energy through fusion reactions of gases, and in the Sun's case, it turns helium into hydrogen and emits light. The size or radius of the Sun is 396,340 kilometers, and it releases an estimated 384.6 yotawatts of energy in the form of other radiation. The Sun's color may appear to be yellow, but when traveling into space, it appears white, and this is because it is made up of all the colors on the radiation spectrum mixed together. It appears yellow because the higher spectrum photons are more likely scattered and thus making it more red and yellow. The Sun emits only 3 types of electromagnetic waves: 49.4% infrared, 42.3% visible, and only 8% ultraviolet. Stars are classified by many things, such as luminosity, radius, mass, temperature, and their spectra, the elements that they absorb. There are 7 main types of stars: O, B, A, F, G, K, and M, with O being the hottest and M being the, gradually getting not as hot. Using the Sun as an example, it's classified as a type G star and has a surface temperature of between 5,000 and 6,000 Kelvin. Mass, radius, and luminosity of all stars are measured in terms of the Sun's units, because otherwise it would be way too big. Using type O as another example, the hottest type of star, it has surface temperatures of over 25,000 Kelvin, and the average mass is 60 times bigger than the Sun, with the average radius being 15 times bigger than the Sun, and the luminosity is a whopping 1.4 billion times bigger than the Sun. Type B, and especially type O, are quite uncommon in the universe though. Moving on to nuclear fusion is known as the energy source of stars. During the process of nuclear fusion, many nuclei of particular atoms combine to make a larger one, and this process releases a lot of energy. This process mainly occurs when converting hydrogen into helium. Where E equals mc squared comes in is that the combined nucleus after the fusion is smaller than the combined nuclei of the atoms beforehand. The difference is the mass converted into energy, and this is done by the equation E equals mc squared. Whilst the star is enduring the process of nuclear fusion, they fuse hydrogen into helium and continue to do so until the hydrogen fuel runs out. The difference for various star sizes is that the fusion reaction happens quicker in bigger stars than it does in smaller ones. So bigger stars burn hotter with a white or blue light, as well as burning for a shorter time. Smaller stars, on the other hand, burn for much longer times and don't burn as hot, with usually a red or orange light. Our final topic today is stellar life cycle. So first of all, we've got the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is a tool used by astronomers to classify stars according to their luminosity, spectral type, color, temperature, and evolutionary stage. The diagram stems heavily from the process of nuclear fusion and hydrogen burning. The main sequence lies in the middle of the diagram, moving from spectral class O to M in decreasing in luminosity. Stars featured in the main sequence are in a stable phase of hydrogen burning for their specific mass. After the hydrogen burning runs out, the stars leave the main sequence and head towards the red giant branch. Many of the bigger stars, class O and B, can also become red giants, depicted in the top right-hand corner. The bottom left-hand corner, however, are for white dwarfs, and these are stars that have finished the hydrogen burning stage and have gotten rid of most of their outer material to create a planetary nebula and are significantly dimmer than other stars in their class. The formation of stars relates in many ways to the formation of galaxies and planets. There are many theories to how galaxies were formed. One such states that galaxies were born when vast clouds of gas and dust collapsed under their own gravitational pull, allowing stars to form and eventually leading to planets. Galaxies and stars within galaxies are still being formed to this very day, and this is mostly due to gravity. Due to their huge size, galaxies also have massive gravitational pull and are slowly attracting each other and will eventually merge. When galaxies get close, gravity pulls them together, causing a collision. Following a collision, stars and other materials begin settling into orbits around the new galactic core. Moving on to future scenarios for stars, there are three main ones: white dwarfs, neutron stars, and black holes. White dwarfs are stars that have finished the hydrogen burning stage and gotten rid of their outer material to create a planetary nebula, and this decreases their luminosity compared to other stars. I think I mentioned that before, but here it is again. A neutron star is a collapsed core of a massive supergiant star, which had a total mass of between 10 and 25 solar masses, but now has collapsed and typically have about 1.4 times the mass of the Sun. Neutron stars are created when giant stars die in supernovas, and their cores collapse, with the protons and electrons melting together to form neutrons. Black holes are regions of space-time where gravity is so strong that nothing, no particles, or even electromagnetic radiation can escape from it. Black holes form when very big stars collapse at the end of their life cycle. After a black hole is formed, it can continue to grow by absorbing many objects or other masses from its surroundings. The event horizon of a black hole is linked to an object's escape velocity, basically the speed that something would need to go to escape the black hole's gravitational pull. The closer something becomes to the black hole, the greater speed it would need to escape the massive gravity that the black hole possesses. The event horizon is the glimmer or light around the black hole, where the escape velocity surpasses the speed of light, meaning you would need to be going at an incredibly fast speed to escape. The Schwarzschild radius is the radius of the event horizon surrounding a black hole. The equation for this corresponds to the radius defining the event of a Schwarzschild black hole. The equation goes by Rs equals 2 times Gm divided by c squared, where Rs equals the Schwarzschild radius, G equals the gravitational constant, M equals the mass, and C is the speed of light. Moving on to gravitational fields of black holes, they have many different effects on space and time. A gravitational field is a force that sees massive bodies extend their pull into space around itself, producing a force on other close objects and bodies. The Earth's gravitational field, for example, is what keeps the Moon in orbit around the Earth. In a black hole's case, the gravitational pull is so strong that even light cannot escape. The gravity is so strong because all the matter has been sucked into a tiny space. Now for the Milky Way galaxy, it measures to be over 100,000 light years in diameter, but this is not even close to the size of some of the other galaxies in the universe. A galaxy called M87 measures a whopping 980,000 light years in diameter, and another galaxy, Hercules A, measures 1.5 million light years across. Though these bigger galaxies exist, the Milky Way is still considered a big galaxy overall. Now moving on to shapes of galaxies, there are 4 different types: spiral galaxies, lenticular galaxies, elliptical galaxies, and irregular galaxies. It is estimated that more than 2/3 of all galaxies are of the spiral variety, while the overall biggest type are elliptical galaxies. The different colors of each galaxy depend on the color of the stars featured within it. The Milky Way, for example, is white. Astronomers determine the age of stars by observing their spectrum, luminosity, and motion through space. Each element absorbs light at a specific wavelength, and this is unique to that atom. When astronomers look at an object's spectrum, for example, they can determine its composition based on these wavelengths. The most common method astronomers use to determine the composition of stars, planets, and other objects is spectroscopy. And for a bit of a recap on that, is the interaction between matter and electromagnetic radiation that is derived from wavelength and frequency. Okay, so here's something a little bit different. It's time for a bit of quiz time with Ryan. Alright, so here's how it's going to work. I'm going to put a few questions on the screen for you that are all going to be related to the information I've just told you. I'm going to give you a few seconds to answer them, and then I'll reveal the answers. If you get all of them right, you're clearly a top student. If you get none of them right, then you should probably question why you're doing physics in the first place. Alright, let's get started. Okay, so the first question is, which one of these is not an electromagnetic wave type? The answers are on screen. I'll give you a few seconds. You might want to pause the video maybe. Alright, so the answer to this one was C, ocean waves. If you got it right, good job. You didn't, then not great, I guess. The second question is, what is the surface temperature of the sun? The answers are on the screen. I'll give you a few seconds. Okay, that should be good enough. So the answer was A, between 5,000 and 6,000 Kelvin. Good job if you got it. The final question is, which of these is the correct formula for Schwarzschild radius? The three answers are on screen. Good luck. Alright, that should be enough time. The answer was C. It's all about the symbols with this one. C has the correct set of symbols. Alright, that's it from me. I hope you enjoyed this. Thanks for watching, and I'll see you in the next one.